Alrighty, y'all. Today we're taking a look at translating physics problems into solvable algebraic equations. So for each of these, I'm just going to pick a few problems from recitations and homeworks, and we're going to set them up like this, figure out what do I know, what do I not know, and figure out what it is I'm solving for and what the information is actually telling me. All right, so I have my handy dandy picture sketched for this problem already. You should recognize this problem from your homework too. All right, but we have Teddy the dog jumping off of a platform into the water, landing a distance d away, and the platform is, I'm just gonna call it h, but really we're given that it's 2 meters. Right? So in this problem, based off of how I set my coordinates like this, I know x naught, and I know y naught, and I know my v naught y is 0 meters per second because of how my initial velocity is angled. So I'm told that we move horizontally when we leave the ground, which means that the only component of my initial velocity is in the x direction. There isn't a y component of it. I don't know vx of t and I don't know vy of t, but I know my acceleration in the x is also 0, and I know my acceleration in the y is negative g. And the reason it's negative g is because I said up was positive y, right? And I don't know time. So I have some knowns and I have some unknowns, and now I have to figure out, for part A, what am I solving for? All right, so we can use that kind of sentence structure that we've been talking about. So how fast was Teddy moving when he left the platform? So we're going to do a what is the value of blank? And now for this type of problem, right, we're solving for the velocity when I'm leaving the platform. So I'm solving for my initial velocity. I'm solving for an initial condition. So in this kind of case, my sentence structure would be, what is the value of blank so that, or such that, something happens, right? Okay, so I want to know what do I know to be true about the situation with the dog, and what velocity will make that happen, right? So when it's what is the value of blank, it's what am I solving for? So this one's pretty easy. What is the value of v naught? In the end, I will write v naught equals and circle that answer, and that will answer how fast was Teddy moving when we left the platform. But now it's a little bit trickier to figure out what is happening. What do I want to happen? After we leave the platform, what do I want to happen as a result of this specific initial velocity? Well, I know that I want the dog, Teddy, to, land on top of the ball. So there's two pieces to that. He's landing, and he's also on top of the ball, right? So we'll start with him being on top of the ball, or in the same location as the ball. Well, that means that my x of t, or my position at some time t, if he's on top of the ball, x of t is going to equal that distance. Right? So this is how I communicate with algebraic variables that he's on top of the ball. But I know that has to happen at the same time that he is landing. So x of t is going to equal d at the time, I did not leave myself enough space, when, right? Now I have to think, how do I know that Teddy has landed? Well, when he hits the surface of the water, so when y is 0. So when y of t is 0. Okay? And now baked into this sentence structure helps us a little bit with how we're going to solve this problem. So I want to set x of t equal to d at the time when y of t is 0. So first I have to find the time when y of t is 0. So I'm going to set up my y of t equation. So y of t equals y naught plus v naught y t plus 1/2 ay t squared. Right? And again, I knew my y naught, I know v naught y, I know ay. And now I set y of t equal to 0. And I'm going to solve this equation for t. That gives me the time when y of t is 0. And now I'm going to use that t and plug it into my x of t equation. Equal x naught plus v naught x t 1/2 ax t squared. And again, I know ax. I'm trying to solve for v naught x, which is just going to be v naught, right? Because the first thing I need to do is break that initial vector into components when I'm doing all this algebra. I know x naught, and now I set my x of t equal to d at that time. Right? So I find the time when, I solve for the time when y of t is 0, and I plug that in to my x of t equation and set my x of t equal to d. Right, so this sentence structure kind of instructs us on how to proceed with solving the problem. And that's something that we will see as we keep going. Now we want to know, how fast was Teddy moving when he landed in the water? Well, again, how fast was I moving? Well, that would be what, I don't know why it turned fuzzy, is the value of how fast was he moving? That would be my velocity. Right? And my velocity at the time when he hits the water. Right? At the time when, right? And in this case, I would just want to know the velocity when he's landed. And we already talked about, how do we know when he has landed? Well, that's when y of t equals 0. So again, baked into this question, I have to find the time when y of t equals 0. Right, before I would have solved for it, up here and then plugged in down here. So now I can use that same time, the time that he has landed, plug that into v of t. I have to set up my v of t equations because I'll have to solve for my vx and my vy independently and then combine them back together. So my vx of t is v naught x plus ax t. Vy of t is v naught y plus ay t. Right. Now, because I solved for it up here, I know v naught x, and I obviously still know my ax and my ay, and I know my v naught y. So all I have to do is take that time, plug it in down here, and I can solve for my x and y components. And once I do that, I'll have an x component, vx, I'll have a y component, and I'll add them together to get my resultant velocity vector. Right? And also, it's asking, in what direction is Teddy moving when he splashes into the lake? Well, that would be the other part of our vector, because before we just would be reporting the magnitude, and our direction would be some angle theta somewhere on this triangle. So we could say theta below horizontal, or if I wanted to use this angle, I could say theta away from vertical, right? Vertical, horizontal. All right, so, and that would take the same structure. What is the value of theta at the time when y of t equals 0? Right. So that's the setup for this one. Now, our recitation from this week, a hiker crossing a stream. So again, I'm just going to sketch my picture of this problem real quick. I have bank the river, and the water in between. I know that I'm throwing I can draw that better. All right, I'm giving the boot some initial velocity at some angle theta. I know the trajectory is going to look something like that, maybe. I know that there's a distance d that is being traveled, hopefully, and I'm going to set my origin right here. Again, my leftmost and lowest point in the problem. I'm going to say up and right are positive, x and y. And I think that's everything we were given. Yes, excellent. So I've drawn my picture, set up my problem, and now I want to set up a sentence in terms of algebraic variables that answers my question. All right. So again, I'm going to steal my list of algebraic variables from over here, just so I don't have to rewrite them. And I'm going to erase the what we know, even though a lot of it could be the same. Ooh. Trying to grab it without moving anything else. But by nature of where I set my origin, I know my initial x and y positions. And now I don't know my initial velocity because that's what we're trying to solve for. But I do know that my x and y velocities will be, in this case, v naught cosine theta and v naught sine theta. Now I always recommend setting up your initial velocity triangle, saying here's my v naught, here's my v naught x and my v naught y, here's theta, here's my 90-degree angle, and sine of theta is v naught y over v naught, and cosine theta is v naught x over v naught. This is something that I would definitely want to show on an exam, showing that this is how I'm breaking up my velocity triangle. And I also want to be very careful because I want to make sure that I'm setting this up right? V naught x isn't v naught over cosine, and in this case it's not v naught sine, right? So just to make sure that I get that right, I would normally set this up, but I was just skipping steps real quick. Then I also know my acceleration in the x and my acceleration in the y, right? My acceleration in the y is negative g. I don't know my time, I don't know my final velocity, and now we're going to look at a little bit of these other things because we need to set up our sentence of what we're solving for. So in this case, we're solving for v naught. So what is the value of v naught? And again, since I'm solving for an initial condition, my sentence is going to be, what is the value of this initial condition so that something happens? In this case, I'm trying to find the minimum velocity to throw the boot to get it across the stream. Right? What velocity must we throw the boot with in order to get it across the stream, in order for the boot to land on the other side of the river, over here? And again, like we talked about with the dog, there's two parts to that. There's the landing, and then there's the being on the other side of the river. So if it's, how do I know that it's on the other side of the river? Well, x of t will equal that distance. I should make that red to fit what I've been doing. All right. What is the value of v naught so that it gets across the river at this time when? Right? So it has to get across the river and also land back on the ground. Right? So that's how I get my x of t and y of t. And I follow the same procedure as the first part of the problem with Teddy the dog, where I solve for the time when y of t is 0, and I plug that in to my x equation set equal to d. Because I'm finding the time when y of t equals 0, and if I were to get a value for that time, then I would be plugging a number into x of t. But in this case, we're going to get an expression of t in terms of my initial velocity, so that when I plug it into my x of t, I'm not plugging in a number, but I'm plugging in something that only depends on v naught, so that my final equation will only depend on v naught, and I can solve that equation for v naught. Just realized that I'm a question mark. Okay. Now similarly, if we accidentally throw the second boot with the same initial velocity but a different angle, where will it land? Right? So now, given v naught and a new angle theta, where will it land? So what is the value of, well, if I'm being asked where it lands, we said that my x position determines if it's landing in the river, on the other side of the river, or further. So what is the value of x of t? And how do I know that it has landed? At the time when y of t equals 0. Right? So again, I want to find my position, or where it lands. Right? So when we're breaking up our question like that, we're thinking, what am I solving for? How do I define where something is? And how do I define that it has landed? And again, same thing. In this case, I could solve my y of t for time, but I'll, very similarly to how I did before, I can solve my y of t for time, but this time I'll know v naught, so I can solve directly for time. And then I plug into my x of t equation and see, instead of setting x of t equal to something, I can plug in my time, and since I'll have my v naught, the only unknown will be x of t, and I can just evaluate that expression for x of t. Right. Then on to question 2 from that same recitation, and this one is just writing a bunch of sentences for us. But we're given a whole lot of variables to describe our situation here. So we're on the roof of a snow-covered building, so I'm going to draw my building and the ground below it. Trying to hit a friend with snowballs, walking on the quad, throw at an angle of that with a speed of that, and a height h. So I can define the height of the building as h. I can draw my initial velocity vector at an angle theta, and it's an angle theta above the horizontal. All right, so whenever we're given a theta, we want to be thinking about where it's given between, right? It'll be given of a vector if it's a vector above the horizontal, or it could be a vector or an angle from vertical, right? So we have to be careful about that, because that just affects how we set up our triangles, right? But our general trajectory might do something like that. And then our origin, I'm going to place, again, down here. So I like to put it, again, at my lowest point and leftmost point of my problem. Doesn't matter where you put your origin. I just like to do it like this. And that is it. That's everything we were given. We weren't given, I don't believe we were given a distance d this time. That's fine. Right. Oh, because we're solving for it later. Right. So, again, I'm going to paste my kinematic variables over here. And because I set my coordinate system, I know my initial x is going to be 0. My initial y is going to be h. My v naught x, I'm given my angle theta and v naught. So even though I don't have a number to plug in for v naught, I'm still considering that something that I know. So if I say that's v naught cos theta and v naught sine theta, those are both known values that I can plug in. Eventually I can, if I was given numbers for it, I could plug those in. I also know my ax and my ay, just as usual, my AX for a kinematic problem for an object in free fall. AX will be 0, AY will be negative g because I set up to be positive. And I don't know time. In fact, we're solving for that, right? So we want to know how much time does it take for the snowballs to hit the quad? Well, again, I'm going to set up my sentence. How much time? What is the value of t? Right, there's my time variable. And what is the value of t when what happens? For the snowballs have to hit the quad. Well, how do I know that the snowballs have hit the quad? How do I know that they've landed on the quad? Well, my y of t is 0. The value of t at the time when y of t is 0. Okay. So this one, I could just set up my y position equation like I did before. I could plug in all of my known values and solve directly for time from that kinematic equation. Now when we're asked where do the snowballs land on the quad, all right, well that would be same way when I was asked where the boot lands on the other side of the river or in the water, my where, I would define that with x of t. So the beginning of my equation, the beginning of my sentence is what is the value of x of t, right? That would define where the snowballs land. And how do I know that they have landed? Well, same thing as before. At the time when y of t is 0. Right? So I would solve for the time when y of t equals 0 up here. And there's the time when y of t equals 0. I could plug that into my x of t equation down here and solve for x of t at that time. Now I need to know how fast are the snowballs traveling when they hit the quad. Well, how fast something is traveling, that's its speed or its velocity. So what is the value of my velocity vector? What is the magnitude of my velocity vector? And again, when they hit the quad, at the time when, well, at the time when they hit the quad, but how do we write that in terms of our variables? Y of t is 0. Okay. And again, same thing we talked about for Teddy the dog. This would be setting up my Vx of t and my Vy of t equations, plugging in my known values and the time when y of t equals 0. Then once I had x and y components, using Pythagorean theorem to get the magnitude of the resultant vector. And again, same thing, in what direction are they moving? I'll have my two vectors and I'll have some resultant. I can define this angle theta, right? So the way I could phrase this sentence would be, what is the, this one's shaking it up a little bit, but it's the direction of the velocity vector. Again, at the time that it lands on the quad, so at the time when y of t is 0. Right? So we can refer to this theta, so I can say, what is the value of theta if I draw my triangle out like this? Or I can ask myself, what is the direction of the velocity vector? Right? And that's defining it the same way. It's theta degrees below the horizontal. So this is another way of phrasing this. It's a little bit less directly algebraic variables the way we've been doing in the past of here's the thing I'm solving for. But that's just because direction's a little bit trickier to communicate. We can't just say theta equals whatever it is at the end and circle it. We'll have to say theta at an angle theta below the horizontal. or above horizontal, or to the right of vertical, to the left of vertical, or from vertical, right? So my direction, I just need a little bit extra to communicate that. Right? So our last one for today is another one you should recognize from homework 2. A hiker standing on top of a mountain with a slope of 45 degrees, kicking a rock horizontally off the top of the mountain with an initial speed v0, sails through the air and lands on the lower slope. So, drawing my picture of this, I can have my mountain, and my iPad automatically locks into 45 degrees, which is helpful. I have my initial velocity going horizontally, like that. I know that this angle, all right, we're given the slope of the mountain to be 45 degrees. So my trajectory might do something. Maybe if I could draw a nice parabola, this would work. Something like that. It's not quite good, but we can pretend it is. That's not the important part of this. Okay. So we are given the initial speed v0. Even though we're not given a number for it, we're told that it's at an initial speed v0, which means that's a known value. So when I paste my kinematic variables here, I'll know my I'll know my v0 y, because it's going horizontally, will be 0. And I'll know my v0 x will just be that given v0. So that's already 2 things that I know. Now, like I usually say, I like to set my coordinate system at my lowest and leftmost point of my problem, which means I'm going to set it down here, right, with, we're going to say a positive x going that way and a positive y. Actually, let's shake this one up a little bit. I'll put my origin up here for this one. And just because we're shaking things up, we'll say down is positive. Now, there may or may not be a reason that I'm choosing this specific coordinate system. Usually I say lowest and leftmost point on in my problem, but this time I'm just picking a coordinate system because I know this problem and I know what's going to help me out a little bit later down the line. Also, if I set my coordinate system down here, then I don't know my initial y position at all because I don't know how far down the slope it's landing. So in this case, I wanted to set that there because I didn't have enough information about where we're starting. So this way I set my axes so I know x0 and y0 are both going to be 0. Now, same thing as always, I know my ax and my ay as well. And I don't know my velocities and I don't know my time. I don't really know my final positions just yet. Now, part A is asking exactly what we've been doing, writing these translational sentences, right? How do we describe the rock lands back on the slope? And it says it'll help to draw a picture. So fortunately, I've drawn us a picture. So I need to think about, how do I know that the rock is back on the slope? Now, the triangle that I've sketched here, I have 45 degrees over here, 90 degrees over here, which means that this angle is also going to be 45 degrees because of the nature of triangles, right? My angles all need to add to 180. And also a 45, 45, 90 is a special kind of right triangle. It's an isosceles right triangle, which tells me something very special that any point on this slope will have. Right, so if I picked this point instead, right, maybe I drew my trajectory too long and it actually lands here, I could still draw the same triangle, the same isosceles triangle, which tells me that anywhere that I land on this slope, my x-coordinate from my origin, my distance this way, has to be the same as my y-coordinate or my distance this way. Right, my y-coordinate has to be the same as my x because it's that isosceles triangle. So that's kind of the trick to this one, is recognizing, oh, 45 degrees, that's where it's landing back on the slope. That gives me my isosceles triangle. X of t will equal y of t. So when the question asks, where on the slope does the rock land? Well, I'm going to define something new. I'm going to say that my distance along the slope, I'm just going to call that d. Right? So there's a few ways you can describe where on the slope it lands. I can find my x-coordinate and say it lands this far this way. Or I can find my y-coordinate and I can say it lands this far down. Or I'm going to say that I want to find this distance d, which is my distance from where I started along the slope. That's just how I'm choosing to define it. As long as it's clearly defined, and when you circle your answer, you make it clear of what you chose to solve for, to define where on the slope, because it is a little bit vague, it's a little ambiguous. Right? As long as you define how you're answering the question, it should be fine. Right? But I'm choosing to do this. So when we're asked where on the slope does it land, I'm solving for what is the value of, keep my color scheme, d at the time when, right? So now it's saying, okay, the value of d, how do I know that the rock has landed? Well, at the time when x of t equals y of t. And that's also partially why I chose down to be positive, because the way that I drew my picture, my x will be in the positive direction, and now my y will also be in the positive direction when it's down the slope like that. So I didn't have to say x of t is negative y of t, right? It would work the same, but I just like to keep it simple so I don't have to deal with those minus signs. So at the time when x of t is equal to y of t, right? So the way I would go about solving this, again, kind of embedded in this, I use these equations. I set up my x of t and y of t kinematic equations, and I find the time when x of t equals y of t. And then I can use that time, plug back into my x equation to solve for my x, use the same time, plug into my y equation to solve for y, and then I can say that Pythagorean theorem, d squared will be x squared plus y squared, or d will be square root of x squared plus y squared, right? And that will be me answering my question of what is the value of d when x of t equals y of t, right? And because my kind of hint that I'm using my position equations is not only just in this sentence, but it also is in my known variables, right? Because my velocity here, I don't know it, and I'm not trying to solve for it. I don't really care what it is. And same with my velocity in the y direction, right? So that kind of eliminates using either of our like vy of t or vx of t equations. Right? I don't really care what my vx and vy are, so I'm not going to be solving for them. Right? And also that other kinematic equation, my vf x squared minus v naught x squared equals 2ax delta x. Same thing. I don't know my v final or my v of t in the x direction, so I don't really care about solving for it. And in fact, I want to know the time when x of t is y of t. Right, so I need to be solving for time, and this equation doesn't even include time. Right, so that's how I can kind of eliminate those, and I know that I want to be using my position equations. All right, well, I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this or anything else that you want me to try to explain, and I will do my best to try to explain it because I guess Sydney explains stuff.